Hi everyone, I'm Layla from Princeton Satellite Systems, and today I will be presenting our compact fusion reactor concept for power and propulsion. So I'll be presenting Starfire. The objective of our Starfire program is to deliver an FRC reactor that is compact in size. We want it to be approximately less than 2 meters in diameter, and we want it to be able to deliver 1 to 10 megawatt of fusion power. Now, because of the high beta nature of FRCs, we want to be using aneutronic fuels. So our aim is to use deuterium helium-3 fuel, and the FRC in our case will be formed using unique radio frequency heating system, which is the odd parity rotating magnetic field that Chris mentioned previously. So the architecture of Starfire consists of a magnetic mirror, so we have superconducting mirror magnets and superconducting coils, linear array of superconducting coils encased with cryostats, which are 16 centimeters thick, which gives us just enough room to have our odd parity RF antennas. For our vacuum vessel, we will have a stainless steel vacuum vessel, but because of the fact that we want efficient penetration of RF, we also want to include ceramic windows. Now, the way our FRC forms, if we take a cross-section in our reactor, the RF antennas generate rotating magnetic fields, which was the green part in this diagram, which induced azimuthal electric field. Now, if we are looking at an example where the background mirror field is going from right to left, we would want the direction of the magnetic field on the right side to be pointing upwards, and on the left side to be pointing in the opposite direction. And the reason for this is that would respect the parity of the FRC, as Chris mentioned before. So this this induces the current loop, which, if we take with consideration to the background mirror field, it would be generating a poloidal magnetic field in the opposite direction. And how this differs from the even parity is the even parity wouldn't respect the odd parity of the FRC, and so hence it would have open field lines, which is where particles would be, particles and energy would flow out. So the odd parity really does ensure that the closure of the field lines, and it allows proper confinement and heating of the plasma. So the plasma regions of interest are the plasma core, and this is where the fusion reactions take place, and the scrape-off layer, and this is where the lower temperature plasma is mixed with ash and it's exhausted. And this is particularly valuable because of the fact we're using deuterium helium-3 fuel. Side DD reactions can produce tritium, which would mix with deuterium and produce high energy level neutrons. And in our case, because our plasma radius is small, the tritium would spin up in high energy, and that would be swept and exhausted in the scrape-off layer, which would prevent this kind of reaction. So the Starfire program has two main milestones. There is the Starfire 1 experiment, this is where we're gonna verify the physics, the plasma physics, plasma confinement, heating, and then we have the Starfire 2, and this is gonna be the full-scale reactor, which would deliver the parameters that I discussed earlier. For the Starfire 1 experiment, we want to be using hydrogen gas to produce a 13 centimeter radius plasma with a bulk ion temperature of 10 keV and 1 times 10 to the power 20 density, 100 millisecond energy confinement time. And we will be using, in our case, LTS coils. And the reason for this is that we found that it would be more cost effective than HTS, and it would produce the parameters we want for the sake of our experiment. And the RF input power will be 300 kilowatts, and this was calculated from the power balance equation. We estimate the loss due to transport and Bergstrom to be around 150 kilowatts, so assuming 50% efficient coupling, it would be 300 kilowatts needed. So for the LTS coil, we are talking to canyon magnet, and they provide both conduction and liquid cooling. The calculated triple product is 1 times 10 to the power 20, and this puts us in the same band as JET and D3D. So this experiment is built upon PFRC2, which Liam will discuss in more detail in the upcoming presentation. So what is confirmed so far in PFRC2 is field reversal and long pulse stability, electron heating, and they managed to raise their power to 200 kilowatts. What's still in progress is ion heating, which is something we hope to accomplish in our case. So for our simulation tools, we would need a variety. As an initial estimate, we would be using single particle modeling to just see if we achieve the range of temperature we need. But for more accurate representation, for our plasma core, because of the fact it is highly kinetic, conventional modeling methods wouldn't work. However, the scrape-off layer, since it's low temperature plasma with higher collisions, it can be approximated as fluid. So these are some unique particle orbits in our plasma core, and we simulated FRC formation in the plasma core using particle and cell methods. So this is an example of a PIC simulation output. The issue with PIC is the fact that it's very computationally expensive, so we are looking at hybrid approaches as well as using any form of optimization possible to reduce the computational time. And this is another example for the fluid modeling of the scrape-off layer. So one thing that we looked at to improve the computational time of PIC is using physics-informed neural networks. And this was a very preliminary study on an electrostatic PIC code where the solver, the electric field solver, was replaced using the physics-informed neural network. Now, how this neural network works is that the loss function would have to satisfy the PDE, which in our case was the Poisson-Boltzmann PDE, and also the boundary conditions are applied in the loss function. So these are some initial results. The loss was about 0.4. The computational time was reduced by 34%. Now this is not significant, but again, this was like a very initial study to see how neural networks can potentially speed up the solving of the complex algorithms. And this was expanded by a research study actually for a full kinetic simulation. And this was very valuable because in this case, if we're not taking into account the training time, if we're comparing like model inference versus the PIC solving, the computational time was reduced by a factor of like 200, which is very significant because then it would allow us to do more optimization and feedback. So these are the critical diagnostics that we have so far. A very important one is the charge exchange recombination spectroscopy, and this is for measuring the ion temperature, and it can also measure plasma rotation. We also use interferometry for density profiles, bolometers for radial power flux, diamagnetic loops to measure the voltage and hence get the change in magnetic flux and extract plasma data approximately. We also have current monitors, RGAs, and X-ray pulse height detectors, which would be used for to approximate the energy distribution of electrons. So far, everything I discussed was for the Starfire 1 experiment, and how the Starfire 2 would build upon this is it would have a cooling jacket, and this cooling jacket extracts heat from the vacuum vessel, and it drives a Brayton cycle. So these are some cooling methods that we are looking into. So for the vacuum vessel, we are looking to use helium or a mix of helium-xenon. For the RMF antennas, we will use water cooling. For the RF windows, this is still under research. And yeah, so the cooling jacket would extract the heat and it would drive a Brayton cycle, which can also be used for the RF drive. And this is a suggested roadmap for the Starfire 1 program. And this is the team. Thank you.